All right, so in this module, we're going to look at a little bit more on how you actually measure activity. And so let's kind of go over again a little bit more about activity. So activity is technically defined by what we call, so by quantity known as Fugacity. So I don't really want to, or have time in this class to cover what Fugacity is. So we're not really going to discuss Fugacity, but what we're going to do instead is kind of jump over that step in which activity is defined by that, and we're going to reach a conclusion in which we define activity based on what we call partial pressures. Because this is a little bit easier to grasp as opposed to Fugacity, unless we have some more time. And so what we're going to do is we're going to measure the partial pressure of a species, I, so we keep using that I terminology, and that's going to be P sub I, and we're going to compare it to the partial pressure at its pure state, pure standard state. And that is 1 atmosphere ATM, or that's the same as 0.1 megapascal, and this is P naught, so the kind of the standard state pressure. And so we define activity as the partial pressure of that species I over the pressure at its standard state of 1 atmosphere. So when we think of partial pressures, we're using that term partial because there can be multiple components, not just I, but there can be others, right? So this is the pressure attributed to that species. So that's why we're using the term partial instead of just pressure. But pressures are something that we can easily measure in engineering. So that's why we're using this terminology. And so we're really comparing a material and it's the pressure associated to that material or species compared to when it's by itself in its pure state at standard state. And so that's where we get this. And so this is basically always equal to 1 atmosphere. All right. So what I want us to do now is to kind of think through this a little bit to maybe better understand the concept of activity. And so what I'm going to do is I'm going to have us sort of consider a hypothetical experiment. Sorry for my handwriting here. All right. So we have a hypothetical experiment. So imagine that we have an evacuated tube. So I'm just going to draw it as a box, right? So there's nothing in this box, right? It's basically an evacuated glass tube. And we place our material, and this is an element M. So just again, just random, whatever it is. So we have a chunk of this metal or this element M, so it's a solid, in this tube where there's nothing else. So there's no air, nothing. And so what we do is we heat this to a temperature, and we just call that T. And what we do is we wait until equilibrium. So we basically wait until nothing's changing. right? So that could be an hour, that could be 7 days, we don't know. But we wait until it reaches equilibrium. And what we do at that point is we measure the gas pressure. So we basically, by measuring the gas pressure in this evacuated tube, nothing else was in there. So if there's gas, it's from the element M, right? And since this is in its pure elemental state, this is going to be our pressure of that metal at that standard. And so this pressure is solely a function of temperature, right? So if something is at low temperature, we would expect that there's not a lot of gas molecules because there hasn't been enough energy to cause them to come off from the solid, right? But as we heat it up and up, we would expect more fraction of that material becomes in the vapor phase, and therefore the pressure in this container would increase. So this pressure of this in its standard state is really just a function of temperature. So it'll increase with increasing temperature. All right, so that's the first part of it, right? So this is kind of evaluating that standard pressure that we're talking about. But now what we want to do is we want to have another experiment. Again, we have that evacuated tube or container. So again, I just draw it as a box. And what we're going to do now is we have a chunk of an alloy. So this is metal M, but it's alloyed with another element N, right? To create, so basically this is a solid that contains both atoms of M, but also atoms of something else we call N, right? So it's got two components. And we're going to do it in such a way where the mole fraction of M is equal to the mole fraction of N, which is 50, right? So it's 50-50 M and N. Right? So we've created a 50-50 alloy of two elements, and so their mole fraction is also 0.5. Same thing, placed in an evacuated tube with no other gases, and then it's raised to temperature T. So same as what we're talking about over here. And so this is where it gets interesting, because we can think of three possibilities of what happens at that temperature. So the first scenario is the fraction of M atoms in the gas phase is equal to the mole fraction of the alloy. Right? Because we have this solid, so when it produces a vapor phase, we would expect M and we'd expect N atoms to go into that gas phase. But they don't have to do so at the same ratio as this. That's only scenario one. So scenario one is that there would be the fraction of M atoms in the gas is the same as the mole fraction. So we'd essentially have 50-50 of M and N in the gas phase. So that seems like that would naturally happen, right? That's what you'd kind of expect. If this is 50-50, if we heat it up, then you would have 50% of the gas is M, 50% of the gas is N. But that's only one scenario, right? That can happen. And so this is known as the ideal case, right? So we talked about ideal solutions. This is an ideal solution. That would mean that the activity of M is equal to the mole fraction of M, which is equal to 0.5, right? So the effective concentration is the same as the actual concentration of 0.5, and therefore that activity coefficient would be equal to 1, right? So that's one scenario. But you might be able to imagine the second and the third case, right? So the second case, this is one where the number of M atoms in the gas phase is less than this mole fraction. In the gas phase. In the alloy. So it's less than 0.5. So in this case is what we call negative deviation. Because it negatively deviates, right, lower than our mole fraction in the alloy. And so in this case, A, the activity of M is, sorry about that, the activity of M is lower than the mole fraction of 0.5. And therefore, when you plug that into the activity coefficient equation, what we see is that this activity coefficient of M is now less than 1. So what happens here, if you think of this on a sort of physical basis, what this implies is that the M atoms would prefer to be in the solid, right, and not so much in the gas. So they prefer being in the solid compared to gas, and vice versa for N, if you want to think of it in that case. But we're just looking at M because we compared it to this experiment over here. All right, so the last part of this, so let's look at one last case here. So case 3. So as you can imagine, if we had up here, we had less, we could also envision a scenario where M is more prevalent in the gas phase than in the alloy. And so that's the third scenario. And again, sorry for the focus here, but the fraction of M atoms in the gas phase is more than that of the mole fraction in the alloy. Excuse me. So it's greater than 0.5. And so this case is called, as you might have guessed it, positive deviation. So positive deviation. And that means that the activity of M is greater now, the effective concentration is greater than the mole fraction of 0.5, and therefore the positive deviation refers to the activity coefficient being greater than 1. And so, again, in physical terms, what that means is if we go back to our example here, right, M actually prefers to be in the gas phase and not in the solid phase when compared to the other component, right? So that's what this implies. And again, we're talking about these deviations because in our first example up here, right, Ideal case, activity coefficient equals 1. When it's less than 1, there's negative deviation. M prefers to be in the solid. In this case, positive deviation greater than 1, and it prefers to be in the gas, right? So that's what it means when we talk about partial pressures. And we kind of envision this experiment up here that we had. And we compare something that's pure state to that in a mixed state like an alloy.